Hi everyone, and welcome to Eric's Electronics Workbench. So quite a while back, this Hewlett-Packard 8561E spectrum analyzer was the subject of a video where I made a modification and did some repairs to the instrument. So I'll post a link to that video in the description below. You may want to check out that video. Now, since the time of that last video, this instrument has been functioning very well until just recently, and now it seems to have developed a problem. So let's get started with the troubleshooting. So the problem that this 8561E spectrum analyzer is having is that the displayed amplitude value is much too low. It's way out of spec. So one of the first things that we can take a look at, grab this little adapter right here, is we'll take a look at the calibration output signal, which is 300 megahertz at minus 10 dBm. So it comes out right here. So let me get a little jumper cable connected here, and we'll go over like so. Alright, so now we'll go to frequency, put 300 megahertz into the middle. Span, let's give the span, let's say 100 kilohertz, like so. Alright, so the reference line at the very top is 0 dBm, and again this is a minus 10 dBm output. So if we go here to peak search, you can see that the marker right now is being displayed up here. It is at 300 megahertz, but it's minus 24.17 dBm. So again, very, very low and completely out of spec. Now this calibration output signal has already been verified and it's known to be accurate. So that indicates some kind of a problem going on with the spectrum analyzer. Now there is a little bit more to it, because let me disconnect this. Oh, one other thing real quick here. I'll show you this. If I go over to the calibration menu, and then it was right there, yep. So reference level adjust, if I hit that. So it says reference level cal, and then it says 220. That's just an arbitrary number, but it can vary over a very wide range, I think up to something over 500. But what that number adjusts when you change that is this point where the peak of the signal touches the reference line. If this was working correctly, it's basically a fine adjust, and so that you can get this peak just to touch that reference line, and you would actually have it set so that the reference line is minus 10 dBm, and then when this is an output of minus 10 dBm and everything touches, you know, it's calibrated. So it's a real easy calibration, and of course it's all relying on this signal being accurate, and it was at one point. So this has always been at 220, and in the past 220 did touch a minus 10 dBm. In fact, what we can do right now is if I go to the amplitude and the reference level, see if I step it down right now, reference level minus 10 dBm, see how it's still shy of touching the top? So now the top graticule going across right there, where it says RL, minus 10 dBm, it should be touching the top, but it's not. And changing that value in that cal menu, it does not have enough range to bring that all the way up. So something is definitely wrong. And again, that calibration value is a very fine adjust, and it mentions in the manual that, in the service manual, that should be ideally pretty close to 0, or, you know, some value in there, but not skewed way off to the end, like 500 or something like that. And changing that value just is not bringing this into anywhere near the correct reading. But that's only one kind of issue that it's having with the inaccuracy on here. So let's take a look at something else. Take this back off. And what I'm going to do is remove this adapter. So I'm going to go ahead and put the amplitude back to 0 dBm. So let's use the signal generator, and pardon the camera movement. So go over here just so you can see the instrument that I'm using. So my Roden Schwartz SME06. So I know there's a pretty bad glare on the screen right there, so pardon that. I really can't do anything about the lights, but I'll be using that signal generator for a few different measurements here, different input signals. So what I will do is grab this coax cable, this channel adapter right here. So I have this power meter sensor right here, so it's a 8482A. And get this coax connected on here. Alright, so coax coming from the signal generator, all connected, adapter on the end right there. So let me move the camera up here so you can see power meter. So that's Agilent E4418B. So I'm going to go ahead and turn on the signal generator. So right now the signal generator is set to 10 megahertz at 0 dBm. So this power sensor has already been zeroed and calibrated for the meter, so everything is preset and ready to go. So you can see the reading on here, again, pardon the camera movement, but very, very close to the 0 dBm, okay? So no issues with that. And over here, just get you zoomed in a little closer so you can see the settings. But you can see right up there, 0 dBm, and it's set to 10 megahertz. Okay, so keeping all of those values in mind, let's take a look back at the spectrum analyzer here. So I will put this adapter on here. There's a little SMA connector on the coax, we'll just use this adapter instead. Turn the signal generator off. Move this connector over here, cable rather. Okay, turn the signal generator back on. So let's go ahead and put 10 megahertz into the center. So frequency center will be 10 megahertz. And the span should be the same. It was 100 kilohertz, no problems there. So you can see this is way out of spec. If I go to a peak search, and it's got the marker right on the peak, so you can see that the marker is showing 10 megahertz, no problems there, but now it's minus 40 and some change dBm. Now, I just showed that it was in fact actually 0 dBm, and the reference line up here is 0 dBm. I mean, that is incredibly out of tolerance and out of spec. Definitely something wrong there. But take a look at this. I'll start increasing the frequency. So what I will do is just jump up here. Let's go to, say, 500 megahertz. And just do frequency 500. Oops. Okay, there's 500 megahertz. So nothing else has changed. The signal generator is still set to 0 dBm. But now look at where we're at here. If you do peak search, make sure the marker's on the peak right there. So now it's telling us that the marker is at minus, or 9.5, right around there. Spot on, actually. Yep, minus 9.5 dBm. So that's a lot closer. It's still not accurate, but it's improved. So now let's jump up to, say, 1 gigahertz. So frequency over here on this signal generator, 1 gigahertz. Frequency 1 gigahertz. Peak search. And now you can see that the level right there is minus 6. Looks like 83, so minus 6.83 dBm. So getting closer to that 0 dBm value. So as the frequency is increasing, the accuracy is improving. Okay, so that's interesting, and that actually tells us maybe somewhere where the problem might be. Now, this particular spectrum analyzer has 2 bands internally inside. One band goes from 30 hertz to about 2.9 gigahertz, and then the second band, band 1, they call that band 0, but then band 1 is 2.75 gigahertz to 6.5 gigahertz. Now, if there's a drastic change when the instrument switches between bands, that can indicate a problem in a specific area or part of the RF path, within the instrument. But that actually doesn't happen. So as you can see, we haven't really crossed over from band 0 to band 1 yet, but it is improving in the accuracy. Now, if I go over here, let's jump up to band 1 and put it, let's say 4 gigahertz, we'll do that. So frequency 4 gigahertz. Okay. So there's 4 gigahertz right there. And if we do a peak search, so it's actually a lot closer now, okay, but it's still down. The marker's at 3 gigahertz and minus 4 dBm, but there isn't 4 dBm of loss in this cable. Now, if I go here, let's see, this power sensor is good to 4.2 gigahertz, so let's take a look and see. Shut this off here. Take this cable back off. Just connect it back over to the power sensor like this. Turn turn this on here and come up here. So you can see now the 4 gigahertz signal from the signal generator going into the power sensor. And you can see the level is actually minus 2.8 dBm. So again, the spectrum analyzer was not accurate in its reading. But it's getting closer and closer the higher the frequency goes. And I've played around with it a little bit, and there's no major change when it jumps from band 0 to band 1. There's no major improvement. It's just a gradual improvement basically across the entire range of the spectrum analyzer. I'm very suspicious that there might be a problem with the input attenuator. So that's, I think, the first place to start looking. And there is one other thing that we can take a look at here. So let me put this back on spectrum analyzer. This is actually something that's called out in the service manual. So let's take a look at something else. So the service manual has a test, and it says to set the center frequency to 0 Hertz, the span to 1 megahertz, and the input attenuator to 0 dB. All right, so let's go ahead and do all of that. So center frequency at 0 Hertz. So we'll do frequency center 0 Hertz. Okay, and the span should be 1 megahertz. So span 1 megahertz. And then the input attenuator is supposed to be at 0 dB. So what we want is attenuator to manual 0 dB, like so. So now what we're actually seeing here is the local oscillator. All right, so that's the feed through from the local oscillator. And what they're telling you is that if the local oscillator feed through amplitude is the specs, so let me look here real quick on what they're saying. Minus 6 to minus 30 dBm. Okay, so if we take a look at the marker right here, so see how the marker is moving up and over that peak right there. So that marker is sitting right at minus 11 dBm. So that's within spec, because they're saying from minus 6 to minus 30 dBm. It says if the local oscillator feed through amplitude is within the limits but signals are low, which that's exactly what we're having, then the RF path following the A8 mixer, so assembly number 8, if that mixer, it's probably operating properly. So that actually eliminates a lot of the internal components, so the problem is likely before the A8 mixer. So let's take a look at the block diagram and see what that actually points to. All right, here's a partial block diagram of the RF path starting at the input connector. So the input connector is right here, and it goes right into this attenuator assembly. And then out of the attenuator assembly, comes over here to the A10 assembly. And A10 is a Yig-tuned filter and mixer. So there's actually a switch, and if the switch is in the lower position like it's shown, it comes down here, and that's the low band, and then the path comes right around, so it doesn't go through any of this. And then there's a filter right here, and it continues over here to the A8 assembly dual mixer. Now it mentioned that if that test that we just did looked okay, that the problem was probably not after this mixer, and that eliminates a lot of components. So it looks like that the problem is prior to that, and if it's just going through this switch, then the next step prior to that, because I believe that switch is working okay, is this attenuator assembly. Now if this switch goes up to the high band, then it goes through the Yig-tuned filter and then passes over here and then over to the A8 dual mixer. So stepping back over to this point, this is the A9 input attenuator. So if we look inside here, the RF input comes over, there's a capacitor, and that can be switched for direct coupling or the AC coupling. It defaults to AC coupling, which is the safest, because in DC, any type of DC voltage coming in, basically it's spec'd at 0 volts, but I think about 0.2 volts or higher is a damage point. So basically no DC voltage allowed, but with the coupling capacitor, I believe it's up to 50 volts that is tolerable, because it will block that. So nonetheless, there's mechanical switches in here. So you have a switch here, another switch, and so on, and then you have the resistive pads that it's switching in and out. And so that attenuator is able to go from 0 dB to 70 dB in 10 dB steps. If there's no power applied to this attenuator, it should have a 70 dB attenuation across it. That's just the default without power. So the next thing that I'll do is disassemble the spectrum analyzer, and let's take a closer look at this attenuator, and possibly just leaving it in place, but taking a measurement over here on its output when we put a known input signal would be a good place to start. All right, so there's 4 screws on the back panel. Remove those. This instrument has the optional memory module, so remove that as well. And then stand the instrument on its front panel, and then the whole cover slides right off the back. So we're inside, and we can start in on the troubleshooting. So as always, if you're following along, you are doing so at your own risk. If you're working on an instrument like this, know that there are elevated voltages inside the power supply on the CRT, the line voltage coming into the instrument. So take care and be safe, because again, you are doing so at your own risk. So let me get you zoomed in a little bit closer here on the RF attenuator, and you can see a little bit better view from this angle. I'm going to reposition the camera in just a moment when we continue on with the testing, because I can't reach everything the way it's set up here, but this gives a little bit better view down into the spectrum analyzer. So you can see this is the RF input on the front panel. I have a adapter connected as well. So on the other side right here, there's a rigid coax that attaches and it loops around, comes right here to the input side of the attenuator, and then this is the attenuator down the side, and the output of the attenuator is right over here. So normally this rigid coax attaches to the output, but I have this coax cable attached, and this will go over to the power sensor when we do the testing. You want to be very careful with these rigid type coax cables, because you don't want to pinch them or stress them in any way. So like this one, for example, just to remove it, I've loosened the other end so that it could pivot upwards. You don't want to bend them or twist them or pinch in any way. All right, so let me position things a little bit different with the camera, and then we'll continue on. Okay, I want to apply a 0 dBm signal into the spectrum analyzer, which will just be going through the RF attenuator, and then we'll measure the output of the attenuator on the power meter. So I have the output from the Roden Schwartz SME06 going into the power meter right now, and you can see it's set to 0 dBm. Now, the actual output from the signal generator is just a little bit higher, just by a very small amount, and it's compensating for the loss in the coax cable between this point and then the output from the signal generator. So that assures that we're getting exactly a 0 dBm input here. So let me go ahead and switch off the signal generator. I'm going to disconnect this coax cable, just move it over to here, so, and remove this adapter. Go ahead and get the spectrum analyzer switched on. The noise you hear is the speaker when it first powers up. Okay, so as soon as this is done doing its initializing and self-test, get things going here. So by putting exactly 0 dBm input, when this steps through the 10 dB attenuation and 20 and then 30 dB attenuation, we'll be able to easily see if those numbers match up over here. Now this power sensor only goes down to minus 30 dBm, so I can't go any further than that, but it'll give us a start. So it looks like it is started up here, and what I need to do is go to amplitude. Of course, it's upside down, so I've got to look at this kind of awkward angle here, but it looks like the attenuator is right there. We'll go over to manual mode, turn the RF output on. Okay, so there's 0 dBm going into the spectrum analyzer, and we do see a negative 10 dBm, minus 10 dBm right there, and the attenuator is set to, what does it say there, 10 dB, so that actually looks like it's working correctly. So if I step this, that is 20 dB, yep, minus 20 dB, and minus 30 dB, it's right at the end of where this can measure, but yeah, we're right there. So I'm really not seeing any issue with that attenuator. It looks like the problem is further downstream in the RF path. So if I go, let's see here, I think we can hit 0, and then dB, that shuts the attenuator off, and yeah, we're right at 0 dB. So yeah, it looks like the attenuator is working okay. For the testing that I was doing initially earlier in the video, the attenuator is set to, minus 10 dB and, some of those values right in there, and it wasn't cooperating at all with the levels that we're seeing on the screen, but in fact the attenuator is working, so the problem must be elsewhere. The attenuator, again, it steps all the way down to minus 70 dB, but no need to try and take those measurements, because I don't think there's anything wrong with the attenuator at this point. So it looks like some more troubleshooting to take a look at what's next to test, and so let me do some more checking, and we'll continue on. So the input attenuator is functioning correctly. It has a flat response to any given frequency. That's exactly what you want to see. So if we take a look, the output of the attenuator goes over here, and it goes to the A10 assembly, which is the switch and Yig tune filter. So there's an RF switch right here, and then you can see this is the YIG-tune filter. And the YIG-tune filter is acting as a bandpass filter, and that's only in use when this switch is in the up position, which is for the high band, and when the switch is in the position shown, that's for the low band. So you can see the signal would come in here, go right down and out for the low band. Nothing else happens within this assembly when it's in the low band. And on this spectrum analyzer, that low band is 30 hertz to 2.9 gigahertz. Now, when this switch is in the up position for the high band, that's 2.75 to 6.5 gigahertz. And then the output from the YIG-tune filter comes down here, it goes over to the A8 dual mixer. And the same thing happens here on the low band. Signal comes over here, goes through this filter, and then over to the dual mixer. Now, you can see there's an overlap in that frequency when the bands change from the low band to the high band. So 2.75 gigahertz to 2.9 gigahertz, somewhere in that range is where this switch is moving or changing position. Now, this is not actually a mechanical switch. This is a solid state switch or an electronic switch, possibly like maybe a pin diode or maybe a FET switch. I'm not really sure. But again, this is moving whenever the spectrum analyzer is sweeping and moving through that band switching point. Now, if the spectrum analyzer is just sweeping in one of the bands and not going through that crossover point, then this switch is not actually changing positions. So I think that what we should try to do is take a look at this switch and YIG-tune filter, but just in the low band position, because there's a huge amount of attenuation in the lower frequencies, which means that this switch would have been in the position as it's shown here. So I think what we should do is connect this to another spectrum analyzer with a tracking generator. So have the output of the tracking generator go into the attenuator. We know it's functioning correctly. And then that signal will come through here. It'll come over to the assembly number 10, but I'll have the spectrum analyzer just sweeping just in the low band so that this is not actually changing position. And then we'll connect the output of this assembly number 10 over to this spectrum analyzer and see what the response is and have an idea if there's a problem going on, particularly with this switch right here. If that looks okay, then we'll continue and move over here. Maybe this filter has an issue, or we'll have to continue on down the RF path. But I think this would be a good place to start, and let's take a closer look at this, because again, we know this is functioning correctly, so we can go ahead and pass the signal through this attenuator. I'm not worried about that now. So let's go over to the other spectrum analyzer and we'll get things set up. Alright, so the output of the tracking generator on my HP 8594E spectrum analyzer will connect to this coax cable right here, and the other end of that coax cable is right here. It goes into the attenuator. Out of the attenuator, comes over here, and it goes into the input J1 on the A10 assembly, which is that switch and YIG-tune filter. So then the low band output is right here, and it's connected to this coax cable, and this will be connecting here, this end connector, that'll go back up to the spectrum analyzer. So we'll be able to see the response through this switch and YIG-tune filter. Now you can see this adapter and elbow connector and everything right here that I have. Normally this coax cable attaches to the output right here on the low band output, and I'll explain what this is about and why I have that there after we do this first test. So let's go up to the spectrum analyzer. I'll get things connected and we'll run the test. Okay, let's get the 8594E spectrum analyzer set up. So I'm going to grab this adapter and put this on this tracking generator's output. This gives us a VNC connector that we need. So if you're not familiar with what a tracking generator is, the output from the tracking generator follows whatever frequency the spectrum analyzer is sweeping at. So the output from the tracking generator goes into the device that you're testing, and then out of that device you go back into the input on the spectrum analyzer, and then you're able to see the response on the display. So keep in mind that on the spectrum analyzer, this is frequency on the horizontal axis and the vertical axis is amplitude. So, for example, if you had a piece of very high-quality coax, maybe a short section just from the tracking generator over to the input, basically a flat response. Again, if it's very high-quality coax, no attenuation or very negligible for a short section, you'd actually just see a flat line or very nearly a flat line. But let's say you had a very lossy piece of coax that you connected between the tracking generator and the input. And as the frequency increases, there's more and more loss. You'd actually see a line that starts like this, and then it would go lower as the frequency increases. So many different devices have different types of responses that you would expect to see, and it can indicate problems. You could use this to test an amplifier, for example, or bandpass filter, notch filters, many different types of devices. So in this case, we're going to see what the response is through this assembly number 10, which is a switch and YIG-tune filter. We're only testing the switch, not that YIG-tune filter at this point. And the switch should have a flat response, so ideally we're going to see just a flat line. So let me grab this coax and connect it over here. And the other coax needs to go back to the input right here. So, okay. So I think the frequency we can sweep, let's do a start at, let's say, 1 megahertz. That should be perfectly fine. So we'll go 1 megahertz. And let's stop the sweep. Let's just do it at 1 gigahertz. I think that'll be okay. The low band extends a little bit higher than that, over 2 gigahertz actually, but this will be okay. And then let's go over here and set up the tracking generator. So go to auxiliary. We're going to go to tracking generator. And it looks like the output power right now is at minus 40 dBm. Maybe a little bit low. Let's just go maybe negative 30. It's probably okay. We don't want to go too excessively high. We don't want to risk damage, in any devices that we're testing. But let's try, let's say 30 minus dBm, like so. And that go ahead, and that actually turned it on when I entered that value. And that doesn't look right. That definitely is indicating a bit of a problem. So look at how much attenuation there is on the low frequency, and then it comes up here and begins to flatten off. So we put the marker on here and let's get an actual reading. So the marker is this little diamond-shaped symbol. So if I go over here, so that right now that's 190. That's 150 megahertz right there. And if we go all the way down, of course, I told it to start sweeping at just 1 megahertz, which is right there at the beginning. But wow, I mean, if you look here, that's almost minus 70 dBm. And remember, the output of the tracking generator was set to a minus 30. And then we come over here, and that's minus 50 dBm. So that's still a huge amount of loss, even though it's leveling off. So there's a lot of loss and a tremendous amount as the frequency, is lower and lower. If I go back over to frequency, I can increase the stop frequency. We can make it 2 gigahertz. Just bump that up a little bit higher. A bit of an odd response going on there. I don't want to do that. So stop frequency, go 2 gigahertz again, and put this back on the marker. Yeah, we got some peaks and valleys in that response right there, going up and down. But that's. Was that about minus 50 dBm, and then it drops down there to minus 55, 56 or so. But yeah, this definitely fits with the response that the spectrum analyzer was indicating earlier in the video, where we were seeing a huge drop in the amplitude, and look at how it rolls off. Let me do this, go back over to frequency, make the stop frequency, let's just go, let's say 500 megahertz. So you can see that curve, how it's dropping off. Go back to marker, put that down there. And it's about minus 70 dBm when we're putting in minus 30. So yeah, that doesn't look right. That's really pointing to maybe a problem with that assembly number 10. Now, the switch that's in there, that RF switch, it has a control voltage, and I think that voltage needs to be checked just to make sure that that's correct and that it's driving the switch properly. And if that voltage is correct, then I really think that A10 has developed a fault. But there is something else that I want to do, and that adapter that I already showed you that was just poking up off of that other rigid coax that was in the spectrum analyzer. Let's go back over to that and take a look at one other test on the spectrum analyzer. Alright, so I have an idea for a test to see if the low band is functioning correctly in the spectrum analyzer after the switch and YIG-tune filter. So this is that RF adapter that I had installed on this rigid coax I said we'd get back to. My thought is that if I insert an RF signal at this point and we look at the displayed amplitude value at different frequencies, and let's see if it remains constant. Hopefully it does. If it remains constant at many different frequencies as we work higher and higher up, let's say we start at 1 megahertz and increase up to 1 gigahertz, if the displayed amplitude doesn't vary, then it really shows that the RF path and all of the components after this switch and YIG-tune filter are likely working correctly. The problem is probably at this A10 assembly. Now I still need to check the drive voltage to the switch. We'll do that after this test. So let me grab this coax cable right here, and I just need to put this little adapter right on the end right here like so, and then reach over here and connect that onto there. All right. So I'm just going to put this out of the way. I think that'll stay there. Now, this is, of course, coming from the signal generator, my Roden Schwartz SME 06 that we used earlier. And I have a DC block on the output of the signal generator. Absolutely don't want to have any DC voltage going into the spectrum analyzer. Be very costly, and damage and other problems would definitely occur. Now, there's no reason to think that any DC voltage would come out of that signal generator, but it's just a good idea, a good practice to have, because at this point we're after the attenuator, which has that blocking capacitor in it. So this DC block is essentially just a capacitor that's in line with this coax. So just a good safety precaution. So I have the output on the signal generator set to minus 40 dBm, a nice, safe, low level. Again, we don't want to increase it too high because we're after the attenuator and everything here. So I think minus 40 dBm should be perfectly fine. So it's set to 1 megahertz. Let me switch this on right there. So 1 megahertz, minus 40 dBm. So we're good to go there. And now, of course, this is upside down because we're working at the bottom of the instrument. So I've got to do everything sort of upside down and looking past the camera here. So let's go to frequency, make the center frequency 1 megahertz. Let's make the span, we'll do that as, let's say, 10 kilohertz, nice narrow span right there. And so we're, let's get the marker on here, do a peak search. So it's reporting that that's minus 30.5 dBm. All right. So that already looks promising because we're at just 1 megahertz and it's able to display with that much of an amplitude. And as you saw earlier in the video, the amplitude was extremely low, as those frequencies were, starting out around 1 megahertz, 10 megahertz, and so forth. So this is already looking promising that it's able to display that high of an amplitude. So let's increase this. Let's just jump up to 10 megahertz. So we'll go frequency 10 megahertz right there. So we'll go frequency 10 megahertz, like so, and just do another peak search, and it looks like the displayed amplitude is minus 29.83. No problems there. So this is already looking very promising. So let's jump up to, say, 500 megahertz. Okay, there's 500 megahertz, still minus 40 dBm on the signal generator. And we'll go over here, frequency 500 megahertz. And peak search. And minus 30.5. So this looks really good. I don't really see any issues now going on with the rest of the RF path in the spectrum analyzer. So let's jump up to, say, 1 gigahertz. Let's try that 1 gigahertz right there. And the frequency, we'll go back over here, go to 1 gigahertz. And do a peak search. And it says minus 31.67. So minus 31.67, 1 gigahertz. I was just writing these values down just for reference. And again, no problems there. That's looking perfectly acceptable. I'm not seeing any problems. So I think the switch and dig tune filter is likely where the problem is. But again, I'm going to measure the voltage on the drive to that switch and just to make sure that those values are correct. So I'll do that next. Alright, let's see if the correct voltage is being applied to the RF switch. So it should be between negative 9 and negative 10 volts DC. Now I have these probes with extremely sharp and small needle point tips on them. So those work very well for reaching very small components and hard to access locations. And I think I can use these to reach right down alongside the wire where it attaches to the top of the A10 assembly and take a voltage reading there. Otherwise I've got to track it back over to the circuit board and take the reading on the board. So I think I can reach it this way. Happens to be the wire with the white and then orange stripe on it. So if I go right down along the side here. Not sure if I can get the reading. Let's try this right there. This heat shrink right on the side there, it's very difficult to get to the pin. I can see it right there. There it is, right there. Yep, that's perfect. No issues with that. So that's the voltage going to the low band switch. So that is correct, and that switch should be turning on and then just passing that RF signal, and it's really not doing that. It's attenuating it, and different frequencies, low frequencies are attenuating more than high frequencies. So I have to think that the switch in Yigtune filter has developed a problem. So with the troubleshooting and testing that I've done on this A10 module, I'm certain that it's defective, specifically the RF switch inside that module. Now, repairing the module myself is just not something that I'm going to be able to do. The internal components are wire bonded and they're absolutely microscopic in size, so it really does require specialized equipment to do any kind of internal work on the module. Now, back in the day, Hewlett-Packard and Agilent Technologies would have serviced this module, but nowadays Keysight Technologies no longer supports it and they won't work on it. So the best chance to repair this instrument is to find a used takeout module. That's exactly what I'll do. I'll get started on tracking down a replacement module. So this concludes the part 1 video on this Hewlett-Packard 8561E Spectrum Analyzer. And if you enjoyed this video, please remember to give it a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Now, in the part 2 video, once I get the module, one of the things that needs to be done is to calibrate the instrument. There are calibration settings regarding this module. So in the part 2 video, I'll go through that entire calibration procedure, and you'll see exactly how it's done. So stay tuned for that. So as always, thank you for watching, and until next time, take care. Goodbye for now.